we present auto-encoding interpretable transformations. Neural networks are a popular way to learn bespoke features. While useful, the encoding is hard to interpret and exploit. For instance, if an oracle rotates or relights this face, we cannot predict where the images land in this feature space, or what relative transformations, if any, connect them. Knowing this information would allow us to infer pose and lighting with minimal effort. Our aim is to have an interpretable feature space that disentangles at least a fixed set of pre-selected transformations. For example, with this single input image, a user or algorithm could manipulate its feature vectors to predictably change vertical scale, horizontal scale, in-plane rotation, or combinations of disentangled transforms at once. To learn interpretable transformations, we insert our new feature transform layer in the middle of an auto-encoded network. With supervision, we force specific world space transformations of the input to predictably project into feature space, like a kind of metric learning. We use circles and spheres as the target manifold. In this example, sweeping through rotation angle traces out a circle in feature space. Circles can be used for transformations other than rotation as well, and are useful because we can have separation between transformation invariant feature lengths and transformation equivariant feature angles. For all our generated results, whether 2D or 3D, we just needed to train on images and their known relative transformations. We used our method to learn interpretable features for the Basel face dataset. The interpretable encoding is followed by a decoder. Given a 2D view of a face, we can rotate and relight it in azimuth and elevation as if we had the complete 3D model. And we can try combinations at the same time. This will break down for transformations beyond those observed in the training data. As well as synthesis, we can use the interpretable feature space to measure transformations via view-invariant scene descriptors. In blue, we see the cosine similarity between two representations of the same face, imaged at different transformations. And in red, we do the same but for two different faces. Ideally, two views of the same person should have the same invariant feature space component for azimuth, for elevation, or lighting. In practice, the invariance is very good for lighting, and it can map rotated versions of a face closer together than disparate ones. Vertical dotted lines indicate the part of a transform space that was sampled during training. We can use the feature transform layer for the ShapeNet dataset too, which contains 3D occupancy volumes. Remember, we are generating these views from a very low dimensional feature embedding, yet we can separately manipulate the disentangled degrees of freedom of identity and pose. Thank you.